systems. Second part. So we are covering this book of ocean engineering now. The second next textbook. And these are chapter names and covering the chapter 7 of underwater system. And then my part is about unmanned underwater system, ROV and AUV. But by discussion session, we already see what is the difference. But as a summary, we'll see what is ROV and AUV, right? So unmanned system categorized or classified into ROV. ROV has tethered. Tethered means the cable is connected. And AUV is a property of no connection. No cable is connected to the system. So they can swim alone. And hybrid system is combined one. So we can say semi-AUV. ROV, it is towed system, but sometimes it can be swimming alone. And then there is another type of bottom crawling. So swimming means not crawling. Okay? And AV is self-propelling, propeller powered. Or ROV also can use a propeller, but also it can be towed. And then underwater glider is one kind of AUV and other types. And the autonomy level is increasing as so that the remote control that human is operating. ROV is usually operated by human, but also AUV can be operated remotely, but there should be a wireless communication. And without any sensory feedback, means feedback coming from the system, AUV. And then there is actuators coming, and then the control signal goes to the actuator to operate. And teleoperation, and the human operator using video and also sensory feedback coming from the system far away. So they control the actuators. And sometimes it assigns small goals. So autonomy is a little bit increased. And semi-autonomous means unmanned system, basically. And human operator intermittently, not frequently, but sometimes they control. So they assign a mission to the system. So we call this is a human-robot interaction system. And fully autonomous system, there is a mission is given, and scope is usually defined, given. But then after that, human intervention is not, there is no human intervention, right? So there is a level of autonomy in this way. So there is a generation of UV technology, first generation, second generation, and third generation. So first generation, low-level controls, teleoperation, and the agent system, and also there is a centralized control. Second generation, there's a intervention capability and task-based control. So task is given, but also small controls there. And agent has a multi-agent system. Several systems is operated by one person. So it can be a cooperative operation with human and also among agent. And now third generation is autonomy is increased and high level control. That means a very top level mission is given. The small level control is made by the system itself automatically. And so mission planning is made by the system. And swarming and then operation, recall, and distributed control. So not centralized control. Each agent has their own function of autonomy. And then the industrial missions given to them, and we can classify based on industrial missions and scientific missions and then military missions to the unmanned or ROV. Okay, so the missions, for the industrial missions, oil and gas field development is a major work. And then underwater CO2 storage system. Nowadays, the CO2 should be reduced in Earth, so that they are collected and then condensed to be stored underwater or on the sea. And renewable energy development, also we need ROV or AUV. And also subsea and also shore underwater construction. So you may see that there are industrial operation of AUV and ROV, and then you see that strong power is needed so that battery cannot be used for AUV. Okay. Scientific missions, oceanographic research, environmental monitoring, bathymetric survey, and archaeology to find out all the history underwater. Military missions, intelligence, surveillance, and reconnaissance. Anti-submarine warfare and mine sweeping or field operation. That means you need to have a mapping, laying, and sweeping mine. That can be good work for unmanned vehicles because it's dangerous for military mission, as we discussed before. Here is the remote ROV for scientific missions or industrial missions. So examples are coming from USOR Oceanographic Institute of United States, WHOI. And depth capability usually up to 6,000 meters or 6 kilometers. And weight is small for AUV. Okay, there is one video, so let's see that. So, please. What's happening? Why is it not writing? Because it is unopened video. Then we go on to next video. Back. Okay, I'll find out another one in the next time. Okay, so this is also example platform for ROV. And So it's one, and also ROV, so 12 million from Korea, Emirates, and also depth capability of 6,000. Weight is a little bit small as usual, 3 ton. And there is another one from Korea that is for deep sea mining of manganese modules. And depth capability is similar, 5 kilometer, 5, 4, 3 meters each. And this is an example of a glider. So let's see the video, or whether, let's see whether it is okay to see. Towfish video.
Than that. It takes about 2 hours for the bluefin to reach the bottom, where it can operate for another 16 hours. On board the RV Resolution in the Boston Harbor. We've come here to see for ourselves how the bluefin AUV operates.
AUVs like the Bluefin 21, they're the tool you would use to conduct a wide area side scan survey in ultra deep water.
Will O'Halloran is a marine operations engineer for Bluefin Robotics, which designs and builds these autonomous underwater vehicles in Quincy, Massachusetts.
If this were a mission, a real mission, what would it be doing?
So the next thing that would happen is the radio instructions we received to that red antenna there. The vehicle would say, okay, I'm going to start this mission. The propeller would spin up and then it would dive.
Here in the Boston Harbor, the water is only about 40 feet deep, which is easily manageable for the Bluefin because this autonomous vehicle is used to working in depth several miles below the surface.
The Bluefin 21 can dive about 2.5 miles, but Flight 370's wreckage in the Indian Ocean may be deeper than that. It takes about 2 hours for the Bluefin to reach the bottom, where it can operate for another 16 hours. It scans the ocean floor as if it's mowing a lawn, using side-scan sonar, which identifies objects that stand out from the seabed.
When it's working with the side scanners, it's not actually taking pictures, right?
No.
It's measuring sound.
Correct. What it's doing is it's converting sound to electricity and then turning that electrical value into numerical values, then turned into an image.
When it returns to the surface, scientists download the sonar data to computers. The results may look something like this.
And what we're looking at here, for example, this is a shipwreck in Boston Harbor, so you can see how it's different than the area around it. You can see there's parts of the steam engine right there. And
if something catches their eye, the Navy will send down a high-resolution camera on the Bluefin 21. It can take black and white photos covering about 15 square miles a day. It's a slow process, moving at just 3 nautical miles per hour, only made worse by horrendous conditions, freezing temperatures, mountainous terrain, and complete darkness. But even diving blind, there is much hope the Bluefin 21 AUV will see something. Randy Kay, CNN, Quincy, Massachusetts.
Hey. Okay, any question on this? So we saw the video on AV or Towfish, and then we go on to another AUV platform. It is from USA, Lumus, and here the weight is very small, 37 kilograms. So you see that it is a battery powered. The maximum operating depth is 100 meter. Endurance, you see that there is no length. It is about hours because it is battery powered. Another one from Norway. It is also small. Maximum operating depth is 1 kilometer, but the endurance is 24 hours with the speed of 2 millimeters per second. And weight is a little bit big, So that 850 kilogram. So it's a little bit bigger than the previous. It is another one from Japan. Weight is 10 ton. So it's some size. Right? And operating depth is 3 kilometer. So it's a big size AUV. And then cruising distance is 300 kilometers. The big one, the other right one is from Korea. It is very small one, 20 kilogram, and cruising distance is only 10 kilometers. Right. So here is another video. It is about glider system. You see from the map that the glider is moving across the big ocean. Atlantic looks like Atlantic Ocean. Okay, so we should go.
Navigation and flotation mechanisms have been checked. Submarine gliders make it possible to collect physiochemical data such as temperature, salinity, and oxygen levels from the sea in an autonomous and continuous way at a high spatial resolution. So SEAB has a fleet of gliders taking samples continuously in the Mediterranean Sea with the objective of obtaining data, so its characteristics may be studied and small-scale variability solved. But do you know how a glider works? The glider is ready to start the mission. The sensors and the navigation and flotation mechanisms have been checked. Inflating the bladder allows the tail to rise up and receive the operator signal. The commands which initiate the mission can be received either locally from a vessel or remotely via satellite. The computer located in the navigation bay calculates the course to start the mission. At the same time, the scientific bay receives the configuration signal and prepares the specific sensors for sampling. The computer, located in the navigation bay, gives the command to move the battery towards the bow and retract the piston, which will permit immersion to begin. During the immersion, the glider is set to collect scientific data. The CTD allows depth and salinity measurements to be made. The fluorometer allows chlorophyll levels to be estimated. The oxygen sensor determines the concentrations of this molecule in the water column. All the data recorded by the sensors is stored on a hard drive. During the immersion, the navigation data is also registered. In shallow waters, the altimeter is used to avoid collisions with the seabed. When the seabed is detected or the depth objective is reached, the navigation bay gives the command to start the ascent. During the ascent, the glider continues to collect data measurements for temperature, salinity, and chlorophyll. The glider makes ascent and descent movements in the water column of between 0 and 1000 meters. On missions which can last up to 2 months, covering 24 kilometers a day in any meteorological conditions. In the case of an emergency or at the pilot's request, the glider emerges to communicate with the base. The bladder inflates once again to receive the operator signal. The glider transmits all the data collected. receives updates for the mission, and uses GPS satellite positioning to calculate its new trajectory before starting a new immersion.
Maximum operating depth is 1.2 kilometer and endurance 30 days, or sometimes it can be years. There's a long range. Right? And then next one is about AUV glide, no, semi AUV, the hybrid type. Okay, so it is about semi AUV from Korea and also USA, and semi-autonomous underwater vehicle for mission. And there is a web address for them. All right, that's it. For, we finished earlier for a short time. Okay. Sorry for my microphone was off for a short break. Any questions? No? Then let me show you the schedule again and can finish up. So the schedule shows that today we have an evening class because I am in Japan now. But next week we will return back to the regular class on the meeting at the classroom on Tuesday, 1 o'clock. And probably on Thursday I will have a same time, but we will have a online class because I may have a travel to Changwon City. So that's why I make it this is as a green class. Anyway, we can meet at the classroom next Tuesday and regular time of afternoon 1 hour, 1 o'clock. All right? No question? Then we can finish earlier day class. Bye now.